We will now discuss importance sampling within the context of path tracing. Importance sampling is a key strategy for variance reduction. In importance sampling, we seek to pick paths based on the energy or expected contributions. You want to place more samples for high energy paths, and you want to avoid picking low energy paths. At the macro level, we can use it to select between reflected versus emitted. Casting more rays towards the light sources is another option we can do. At the micro level, you can importance sample the BRDF for the ray direction. There have been many papers starting in the 1990s and going on until the present day which seek to reduce variance in Monte Carlo rendering. Physically based path tracing approaches with physically based importance sampling is now standard in production rendering. In fact, about a decade ago, I consulted on Pixar's system for upcoming movies at the time, and starting with about Monsters University, the production renderer has used importance sampling. Recall that we can pick paths however we want. The only requirement is that we weight the path contribution dividing by the probability. We have already seen this division by the probability in terms of the weights for emission and reflectance. Again, to recall the idea of importance sampling, you want to place more samples at these peaks than at the valleys. You can handle this by looking at the function f and dividing by the probability. This will ensure that it is unbiased. Here is a simple Monte Carlo path tracer, which I showed earlier. For each pixel, you cast n samples with 50% probability you decide emitted or reflected. You modulate by a factor of 2. In the emission case, you terminate and you return the emissive value. In the reflected case, you modulate by the BRDF and you trace the path recursively. Here is a simple modification one can make to that. You trace the path to find the intersection P prime. If the surface isn't emissive, if emission is equal to 0, which is the case most of the time, then the probability of emission will be 0. Otherwise, let's say the probability of emission is 0.9, you still consider reflection of emissive surfaces. Of course, you don't need to do that, and in the assignment you're not requested to do that, so you can just terminate at an emissive surface. If the random value that you generate is less than P emit, so that ensures which side you're taking, then you go to the emitted path and you return 1 over P emit. That division by the probability is important times the emissive. Otherwise, you're in the reflected path. You divide by 1 over 1 minus P emit, and you generate a random ray in the direction of P prime. Notice that the probability of emission can never be equal to 1. You cannot set this equal to 1 unless you make the assumption that emissive surfaces don't reflect light and you set the reflectance to 0. Otherwise, you always have to give some probability for reflectance. We've discussed macro importance sampling, which is emitted versus reflected. We now talk about micro importance sampling. In particular, we seek to shoot rays towards the light sources in the scene, as well as to distribute indirect rays according to the BRDF. So here is one variation for the reflected ray. Pick a light source, trace a ray towards that light, trace a ray anywhere except for that light. You can do this by rejection sampling. You pick a random direction. If it hits the light, you reject it. And now you divide by the probabilities. For the ray towards the light, you have to divide by the solid angle corresponding to the light source. So that's F over P. And for the ray not hitting the light, you have to divide by 1 minus that probability for hitting the light. And you may need to adjust for a factor of 2 because you're shooting 2 rays. So in this way, you ensure you always trace towards the light source. There is another technique you will consider in the homework assignment, which is something known as Russian roulette. In this case, you need to maintain the correct weight around the path. After maintaining the current weight along the path, you can decide to terminate the ray. The idea for this is that if you have many rays that contribute only a small amount to the path, let's say their weights are 0.05, 0.1, 0.02, ideally you would only want one of those rays to continue. So you determine a probability corresponding to the weight, for example, that the ray continues, and you effectively toss a roulette wheel, or more accurately a random number generator, to see if that ray will actually continue. However, if it does continue, in order to be unbiased, you have to weight over 1 over the probability. Let's see how this works. Let's assume I have a number of rays, and each of them has a probability of surviving, let's say 0.2, 0.2, 0.2, 0.2, 0.2, corresponding to the weight of 1. Now I take all of these and I apply my Russian roulette. What I will end up with is one ray, so perhaps this ray survived and all of these rays were terminated. This ray now should have a weight not of 0.2, but it should have a weight of 1 so that it is unbiased. The way in which we calculate this is, like many things in importance sampling, is simply the weight divided by the probability. In fact, you can verify that this is unbiased because with probability 1 minus p, the ray contributes 0, and with probability p, it contributes weight divided by probability. This cancels out, and the net result is the original weight. Okay? That will ensure that you have fewer rays which make a more significant contribution. Finally, we can put this together and develop a path tracing algorithm that you will actually implement in practice. The earlier ideas were simple ones which build up the intuition, but in practice will not give you low variance. Step 1, you choose a camera ray which goes from the camera to the given pixel. This camera ray can be quite general. It can sample over the spatial locations x and y in the pixel. It can even sample over the lens coordinates, let's call them u and v, for effects like depth of field. You don't need to implement this in your homework, but it is a cool additional effect you could do. And it can sample over the time if you're trying to do motion blur. The initial weight of this ray is equal to 1. The initial radiance contribution is equal to 0. Step 2, you find the ray surface intersection. Step 3, you immediately add the contribution of the light sources. In fact, you could also handle emission in this step. You say L plus equal to weight times the reflected radiance from the light sources. That will be handled essentially using your direct lighting algorithm. But you might, for example, shoot one ray at the light source. And the homework assignment makes it clear what exactly you need to do there. So that gives you the contribution from the light sources, including later on in the path where you are considering indirect light. Then you multiply the weight by the reflectance or the BRDF of the point. You choose a new ray proportional to the BRDF, and now you call the trace path function recursively going back to step 2. So in this way, what we've done is essentially separated the contribution from the light sources from the indirect contribution, and you always add the contribution from the light sources. This is a method which is sometimes known as next event estimation.